translating DNA into proteins. Here is a program using the new version of the subroutine codon to AA given in the previous section, which is used to translate a whole DNA sequence into protein. This program is given the name codon to P. The program translates DNA into protein. The program can be given as use strict, use warnings and first initialize variables. The $DNA variable is initialized with the DNA string and the protein is an empty string and codon is initialized. Now translate each 3-base codon into an amino acid and append to a protein. For this, a for loop is used. The for is specified as $I is initialized to 0 and is compared to the length of $DNA minus 2 and is incremented with 3 each time. $codon equal to substring of $DNA $I 3. $protein dot equal to codon to AA of $codon. Now print, I translated the DNA, which is the DNA variable, into the protein $protein. The output of the execution will look like this. The elements except the loop are seen before. The loop given here is for my $I equals 0, $I less than length of $DNA minus 2, $I plus equals 3. We know that a for loop has 3 parts delimited by 2 semicolons. The first part initializes a counter. My $I equals 0 statically scopes the $I variable, so it is visible only inside this block, and if any other $I exists in the code is now invisible inside the block. The middle part of the for loop tests whether the loop should continue. $I less than length of $DNA minus 2, that is, if there are none, 1 or 2 bases left, it should quit, because there is no enough bases to make a codon. The positions in a string of DNA of a certain length are numbered from 0 to length minus 1. So, if the position counter $I has reached length minus 2, there is only 2 more bases at positions length minus 2 and length minus 1 and should quit. Hence, the test succeeds only if $I less than length of $DNA minus 2. The third part of the for loop increments the counter after all the statements in the block are executed and before returning to the beginning of the loop. The code given here is $I plus equals 3. Here it is incremented by 3 because we consider the DNA 3 bases at a shot. The code $codon equal to substring of $DNA, $I, 3 extracts the 3 base codon from the DNA. The call to the substring function specifies a substring of $DNA at position $I of length 3 and saves it in the variable $codon. Reading DNA from files in faster format. Several biologists and programmers invented different methods to format sequence data in computer files. So, we need to extract the sequence data and annotations from these files, which require writing code to deal with each different format. Some of the most popular formats are: first one, FASTA. It is a text based format for representing either nucleotide sequences or peptide sequences in which nucleotides or amino acids are represented using single letter codes. The FASTA and BLAST, that is basic local alignment search technique or tool, programs are popular. FASTA format is the most widely used format due to its simplicity. Next one is Genetic Sequence Data Bank or GenBank. It is a collection of database of all publicly released genetic data. GenBank is built by direct submission from individual laboratories and from bulk submissions from large scale sequencing centers. Another one is European Molecular Biology Laboratory, EMBL. The EMBL database has substantially the same data as the GenBank and the DNA data bank of Japan, DDBJ, but the format is different. It's a rich format for storing sequences and their associated meta information feature, coordinates and annotations. It also shares data with the GenBank sequence format. Another one is Simple Data or Applied Biosystems ABI sequencer output. This is a DNA sequence data that has just the character that represent bases and no formatting. It is output into files by the sequencing machines from ABI and from other machines and programs. The next one is Protein Identification Resource or PIR. PIR is a well created collection of protein sequence data. PIR offers a wide variety of resources mainly oriented to assist the propagation and standardization of protein annotation. Another one is Genetics Computer Group or GCG. The GCG program from Accelerate is used at many large research institutions. Among these sequence formats, GenBank and FASTA are the most common. FASTA format. FASTA format is lines of sequence data with new lines at the end. So, it can be printed on a page or displayed on a computer screen. There will be some header information like the name of the DNA or the gene it comes from, etc. at the beginning of the file that starts with the greater than symbol. Here is a pseudo code for getting data from a file and extracting sequence data from FASTA file. The subroutine can be given as get data from a file. The argument is the file name. Then open file. If can't open, print error message and exit. If it can be opened, read in data and return the array data. Another subroutine extract sequence data from FASTA file can be specified as the array of the file data in FASTA format is the argument. Discard all header lines and blank and command lines for good measure, and if first character of first line is greater than symbol, discard it. Read in rest of the file, join in a Scala, edit out non-sequence data and then return the sequence. In the first subroutine that gets data from a file, an error can be occurred when the file can't be read. There are different approaches for dealing with this situation. The drastic approach is to exit, or maybe a default file can be opened, otherwise a false value can be returned. The second subroutine takes the array of FASTA formatted sequence and returns just the unformatted sequence in a string. When we try to print the row sequence data, it can be a problem if the data is much longer than the width of the page. Here we design a subroutine that takes as its arguments some sequence and a line length and prints out the sequence, breaking it into lines of that length. The subroutine print sequence can be given as, first of all, the arguments are initialized to the variables sequence and length. Then use strict, use warnings. Now we want to print sequence in lines of $length. For loop is used as for my dollar position initialized to 0, dollar position less than length of dollar sequence and dollar position plus equals dollar length. Print dollar substring of dollar sequence, dollar position, dollar length, then new line. Now we add all these pieces of code so that it can read a FASTA file and extract the DNA sequence data. Then it is translated into protein and prints it out in 25 character long lines. The subroutine can be specified as, in the first section we initialize variables like the array file data and the variables DNA and protein. Now the contents of the file sample DNA are read into the file using get file data subroutine. It can be given as the array file data equal to get file data of sample DNA. Then we want to extract the sequence data from the contents of the file sample DNA using the subroutine extract sequence. It can be specified as $DNA equal to extract sequence of @file data. Now the DNA can be translated into protein. For this we use the subroutine DNA to PEP. It is called as $protein equal to DNA to pep of $DNA. Now print the sequence in lines of 25 character long. For this, the subroutine print sequence is used. It has given the arguments $protein and the length 25. The subroutine to get file data can be specified as, first of all, we want to collect the arguments and initialize to the file name. Then the file data array is initialized as an empty array. Unless open get file data of $file name, print the standard error cannot open file. Then exit. Otherwise, the array file data is directed with get file data. Now close get file data and return the array file data. Subroutine to extract FASTA sequence data from any array can be specified with the subroutine extract sequence. The arguments are collected and initialized to the array FASTA data. Now declare and initialize variables, the sequence, and for each loop is used to initialize the FASTA data. To discard the blank line, we use the statement if $line equal to the regular expression /s star $, then go to next line. Discard the command line which is specified with the regular expression with hash symbol. Discard FASTA header line which is specified with the greater than symbol. Keep line and add to sequence string, else $sequence dot equal to $line. Now remove the non-sequence data from sequence string variable. It can be specified with the regular expression $sequence equal to ~s / /s then /g. Now return the $sequence variable. Subroutine to translate DNA sequence into peptide can be specified with the subroutine DNA to pep, in which the protein variable is initialized and the arguments are collected and initialized to the variable DNA. Now translate each 3-base codon to an amino acid and append to hash protein. The for loop can be specified as for my $I equals 0, $I less than length of $DNA minus 2, $I plus equals 3, and $protein is concatenated with codon to AA of substring of $DNA $I 3. Now return the protein variable. Subroutine to translate codon to amino acid, which is codon to AA, can be specified as the arguments are collected and initialized to the variable codon, and it is converted to uppercase codon using $codon equal to UC $codon, and the hash genetic code is initialized with the amino acid as the value and the 3-letter codon as the key. As with the previous subroutine, the genetic code hash is initialized with the 3-letter codon as key and the corresponding amino acid's first letter as its value, and is initialized from serine to glycine. Then the exists function used to return true if the key $codon exists in the hash. It is equivalent to the else statement in the previous versions of the subroutine. Otherwise, the else part is executed, which is a print statement to print the standard error bad codon. Now the subroutine to format and print sequence data is specified with print sequence subroutine. Here the arguments are initialized to the variables $sequence and $length. Now we print the sequence in lines of $length. The for loop is specified as for my $pose initialized to 0, $pose less than length of $sequence and $pose plus equals $length. Now print the substring as print substring of $sequence, $pose, $length, then exit. Just think that the information contained in the FASTA file sample.dna is as shown in the figure. If so, the output of the execution will be as given in the new figure.